All right, in this chapter we're going to look at how we solve oblique triangles. An oblique triangle is just a triangle that doesn't have a right angle. We know how to solve right triangles. We've known how to solve right triangles for quite a while. We could learn everything we need to know about a right triangle using Pythagoras and SOHCAHTOA, right? The Pythagorean theorem and right triangle trigonometry. So in this chapter we're going to learn how to solve oblique triangles. And the most important thing to keep in mind is that if we have a triangle that is not a right triangle, we cannot use Pythagoras, we cannot use SOHCAHTOA, right? These are only for right triangles. For oblique triangles, we have a couple of tools. One is called the law of sines, and one is called the law of cosines. And we're going to start out with the law of sines. The law of sines will cover these two cases. And in the next section, we're going to learn about the law of cosines, which covers the last two. So here's the law of sines. The law of sines says, suppose I have a triangle like one drawn here, and I've labeled the angles capital A, B, and C, and the sides little a, b, and c, adhering to the convention where side A is opposite angle A, and so on for sides B and C. The law of sines says that the ratio of the length of a side and sine of the angle opposite that side is constant. So A over sine A is equal to B over sine B is equal to C over sine C. So that ratio will never change. We're actually going to begin by deriving this fact, and we'll derive it for like just this pair, but the process to include C over sine C is really similar. So I've got this oblique triangle here, and we're going to do one of our favorite things to do, which is we're going to drop down a perpendicular. So I've dropped down that perpendicular. I'm going to label that length h for the height of the triangle. And once I drop down that perpendicular, now I have two right triangles. Okay, so now that I have two right triangles, right, so one of the right triangles is right here. And the other right triangle is right here. Now that I have two right triangles, I can use SOHCAHTOA on these right triangles. So using SOHCAHTOA, sine of A opposite over hypotenuse is h over b. And that means if I solve for h, that means that the height h is equal to b times sine A. Okay, now let's move over to the red right triangle here and use SOHCAHTOA to find sine of b. Sine of b is h over h over a, and if I solve that equation for h just by multiplying by a on both sides, we get h is equal to a times sine b. So now look at this. We have two expressions for h. Now the height h is only equal to one quantity, so putting these two things together, we know that b times sine A must be equal to a times sine b. Now I'm going to take this equation, I'm going to divide each side by sine A times sine b. We get to do some canceling. Whoops. Sine A with sine A. And we get the equation b over sine b is equal to a over sine A. So we're going to spend some time in this section just working out some examples, trying to solve these triangles. So when we solve oblique triangles, that's true for whether we're using law of sines or later on when we use law of cosines, we keep in mind that these two relationships always hold, that the longest side is always opposite the largest angle, the shortest side is always opposite the smallest angle. And this gives us a bit of a check, at the end, like, does my answer seem feasible? And that's just sort of one thing that I look at when I'm done a problem, is just making sure that that relationship holds. So we're going to begin with a problem with a triangle that's case 2. I know 2 sides and the angle opposite one of those sides. So here I know sides B and A, and I know angle A. And we're going to solve, we want to solve the triangle, which means fill in all the rest of the missing information. And that means that we want to figure out what is side C, what is angle B, and what is angle C. Now, one of the things we want to do, if we're going to use law of sines, in order to use law of sines, we really want to make sure we have a matched pair of a side and an angle opposite. And we have that, right? I know side A and angle A. So I'm going to use law of sines, and I'm going to make sure that I use a law of sines that involves the fraction A over sine A, because I know all the information in that fraction. Next, I want to pick another fraction where I know where only one piece is missing, right? So I'm not going to use C over sine C because I don't have either of those pieces of information. I'm going to use B over sine B because I know side B, and I can use this to help me find angle B. Okay, so now let's fill in what we know. We've got 20 over sine of 65 degrees is equal to 15 over sine B. I'm going to solve, I'm using this, my goal with this equation is to find angle B. First, I'm going to solve for sine of B. I'm going to isolate sine of B, and then I can use the arcsine function. So if I want to solve for sine B, I guess I could do this a couple of different ways. It's in the denominator, and I want to get it out. So I'm going to multiply both sides by sine B, and in fact, let's see, that will get it out of the denominator. So then we have 20 times sine B over sine of 65 degrees is equal to 15. And then to isolate sine B, I'm going to multiply both sides by sine 65 degrees over 20. And we find that sine of B is equal to 15 times sine of 65 degrees over 20. Going back up here to this line up here, you could also, eventually get to that same spot if you said, oh, that's a proportion, so I could take the cross product, and that's fine too. So if sine of B is equal to that fraction, then we can find B by just taking arcsine. That means that angle B is arcsine of 15 sine of 65 degrees over 20. So I'm a fan of just plugging in this expression like right into the calculator as is, and not doing rounding, but sometimes people like to approximate this value up here first. I'm going to do it both ways just to show you. So first I'm going to plug it in like we've written it here. So arcsine, inverse sine of 15 times sine of 65. I'm closing the parentheses on the sine function and then divided by 20. And I get 42.8 degrees. So there's angle B. If you wanted to approximate the value of sine B first, so 15 times sine 65 divided by 20, We get 0.67973. Just don't round that too coarsely. So I'm going to go out, I think, at least 5 spaces. So I'll go 67973. And that means that that B would be arcsine of 0.67973. And we get 42.8. So whether you like to approximate it first and then plug that into your function or not, either's fine. Just if you do approximate, don't round too coarsely. So now, okay, so we know angle B. Now, looking to find side C and angle C, you know, I still have a whole pair. Like there's a pair of a side and an angle, and I know neither. So I'm not going to use law of sines yet to get either of those. But now just know that I know 2 angles. I know angle A and I know angle B. So we could find angle C just by using the fact that all the angles have to add up to 180.
Yeah. So the daily routine, I didn't really know to do that. Not really throughout the day, so it's like brainstorming through something.
So we get 180 minus 65 minus 42.8. We get 72.2 degrees. And now I have 1/2 of this matched pair, 72.2 degrees. And we can use the law of sines to find side C. When I'm using law of sines, I try to use a matched pair that I was given whenever possible. But you could go ahead and use it with B and angle B if you want. I'm just going to go ahead and use A. Side A and angle A, and then side C and angle C. Oops. So plugging in the information, side C we don't know. Angle C is 72.2 degrees. Side A is 20, and angle A is 65 degrees. To solve, we need only multiply both sides by sine of 72.2 degrees. So side C is 20 times sine of 72.2 degrees divided by sine of 65 degrees. Oops. 20 times sine, not inverse sine, but sine of 72.2 degrees. Close those parentheses, divide by sine of 65 degrees. You get 21.0 degrees. Sorry, that's not an angle. So it's 21.0 meters are the units. Okay, let's try another one. We'll do a case 1 example now. Suppose I know 2 angles and 1 side. You know, and I want to fill in all the missing pieces, right? So I want angle A, I want side B, I want side A. So the low-hanging fruit here, what's easiest to get initially is just angle A, because I know 2 angles of a triangle. So angle A is 180 minus 25 minus 108. 47 degrees. Okay. Now, we're going to use law of sines to proceed, and I know a pair, right? The matched pair of a angle and a side opposite that angle is C and side, angle C and side C. So now I'm just going to pick a side to solve for first. So let's say we want to solve for B first. If I want to solve for side B, then I'm going to use the equation B over sine B is equal to C over sine C. I'm making sure I use C over sine C because that's the pair for which I know everything. Now, in the last example, we plugged things in right away and then solved, but you can also do some algebra first. You know I want to solve for side B, so I can see right here I'm just going to have to multiply both sides by sine of B. And we get B, side B, little b, is C, little c times sine of B, angle B, over sine of angle C. So now I'll just plug in my information here. So 59 times sine of 108 degrees divided by sine of 25 degrees. I'm being really careful with my parentheses here, making sure I close out the parentheses on that sine function before I divide. I get 132.8, and that's feet. Alright, so now the only thing we're missing is one side. Be careful and just be kind of mindful and work deliberately through these problems, because often I have seen students say, okay, I know two sides of a triangle and I want a third one, and they just jump right into Pythagoras out of habit. But the Pythagorean theorem does not apply to this triangle. It is not a right triangle. So we're going to find side A, and we're going to do so by using law of sines again. So I'll have little a over sine of angle A is equal to little c over sine of angle C. I can multiply both sides by sine of A. So side A is C times sine of angle A over sine of angle C. And that is 59 times sine of angle A, 47 degrees, divided by sine of 25 degrees. It's 102.1 feet. And that's completes this example. We'll just note that we didn't make this observation on the last one, but I'll just going to stop here and observe that the smallest side, 59 feet, is opposite the smallest angle. The largest side, 132.8 feet, is opposite the biggest angle, and that makes sense. Alright, so now we're going to take a look at a special scenario that can arise when we're solving an oblique triangle. We call it the ambiguous case. Ambiguous meaning it could be one of two scenarios, depending on the information that we're starting with. So the case where we know two sides and the angle opposite one of those sides can sometimes result in ambiguity. We already solved a scenario like this, right? So we said, let's see, we know two sides and the angle opposite one of those sides. And we were, in example 4.1, we were in a scenario where we knew that these two other angles had to be acute. However, occasionally, depending on the information that's given, we may be in a scenario where there's more than one triangle that we could draw that satisfies the given information. So there's, at the heart of this ambiguity is the fact that the inverse sine function will only ever return an acute angle. And when we are given two sides and the angle opposite one of those sides, there may be two triangles that satisfy the given conditions. Using law of sines, we'll generally find one of those, right? And it'll be the scenario where a given angle is acute because the inverse sine function only returns an acute angle. But when there are two solutions, it is the case that one of those angles would be obtuse. And we'll talk about how we find that second solution. But first, we're going to talk about how it could be that there might be more than one triangle. So look, depending on the information given, and here's how I've set it up in these notes. I've set it up in these notes right here, that when we're talking about it, is that the angle that we're given, I'm calling that angle A. Now, that's not all the case in all the problems that we're going to do. In the exercises, sometimes that angle is given will be angle B or angle C, but I'm just calling it angle A, and when I draw it, I always draw the given angle in the bottom left. I find it helpful to be, kind of consistent in how I set it up. So imagine that I'm given angle A down here. I'm going to highlight the given information. I'm given that angle, I'm given this angle, and I'm given side little b and side little a. Now, depending on the angle and the two sides, like the measures, how long those sides are, how big the angle is, it's possible that there might not be any triangle that you can draw at all, right? So if I'm given angle A, imagine this is fixed, right? This angle cannot open or close at all, right? That's like welded in that position. And I have this fixed length here. And then this right here, imagine that that's like a hinge, right? So that this side A can kind of swing back and forth. If A is too short, it might not be long enough to reach the opposite side at all. And so the minimum length A has to be, in order to even make a triangle, is the height of the triangle. It would be like a right triangle solution, right? So if A is shorter than whatever that height that would be to make it a right triangle, you're not going to have a solution at all. If A is exactly equal to that height, then you've got a right triangle. Now, once A gets longer, we've got an obtuse or an oblique triangle. And depending on the range of values that A could take on, you'll either have one oblique triangle or two. So if A is really big, if A is bigger than side B, then it has to extend out. I'm looking at the bottom triangle now. If A is bigger than side B, it has to extend out this way, and you get just one solution. But if A is bigger than the height H, but less than B, there are two possible. So now I'm looking at this triangle right here. So A is bigger than H, which means I could swing it out this way, right? But if it's less than B, I could get another solution if I kind of, again, imagine that this is on a hinge here. So I could kind of swing this side around, and it connects to this side again right here. So it is possible to have two solutions. And the two solutions, I'm going to erase these markings right here, and I'm going to draw them again. I'm going to draw new markings. The two different solutions that we have would be this triangle or this triangle. So the ambiguous case, you know, like does cause some confusion. It seems odd that there could be two solutions, and it takes some getting used to kind of recognize when we might be in an ambiguous case. But note that this only applies to case 2, the case where we know two sides and the angle opposite one of the sides. That's the only case where it could be ambiguous, and the first thing you want to do in that scenario is figure out, well, what is H, right? Like, what is this side H? What would that H be in order to make it a right triangle? And you do that just using SOHCAHTOA, and then you compare the value of the side opposite the known angle to that side. See if you can make a triangle at all, and then go from there. So we're going to do an example here. So here's a scenario where we know two sides, A and B, and I know the angle opposite one of the sides. I know angle A. So I'm going to start by sketching this out. And I'm just not going to sketch the full triangle right now. I'm just going to sketch out what I know. I've got an angle of 26 degrees, which I always draw on the lower left just because habit, I guess. So this is angle A, 26 degrees. And then the known side, side B, I'm going to label that up here, so that's fixed. Imagine that this angle opening at 26 degrees, that's welded in that position. Oh, sorry, not 41 degrees, 41 centimeters, that's not an angle. And that this is a fixed length of 41 centimeters. This length along the bottom can extend, I don't know how long, but like I imagine that I have a lot of space to play with there. And then I know angle A is 25 centimeters. So it's shorter than B. Now, if angle A were longer than B, I wouldn't have to bother with finding the height and seeing if I can make a triangle at all. If the angle opposite my known, if the side opposite my known angle is longer than the other side, then there's only one triangle. But it's shorter than that. So the first thing I have to do is see if I can make a triangle at all. So I'm going to find this height. And I'm going to do that using SOHCAHTOA. Let's find H. So sine of 26 degrees is equal to H over 41 centimeters. And that means that H is 41 times sine of 26 degrees. I get 17.97 centimeters. Okay, so now A is longer than that. That means that this side A is long enough to extend down to meet this opposite side. Right, so A is bigger than H, but less than B. That means that not only is it long enough to extend out, because it's bigger than H, but it's also less than side B, that means that there are two solutions. Right, so there are two triangles. One is the triangle I've drawn here. The other is the triangle I would get if I started up here, right, and drew angle A, or side A rather, so that it came down this way. So we're going to find the acute solution first, where angle B, which is over here on the right, angle B right here, that's an acute angle. So we're going to solve that triangle first. I know side A and angle A, so I'm going to have A over sine of A is equal to B over sine of B. I'm going to plug in the information I have here. So A sine B, or whoops, see, 25 over sine of 26 degrees is equal to 41 over sine of B. I'm going to go ahead and use cross product this time. So I know that 25 times sine of B is equal to 41 times sine of 26 degrees. And dividing both sides by 25 tells us that sine of B is equal to 41 times sine of 26 degrees divided by 25. Okay, now to find to find angle B, I'm gonna just take arc sine of that fraction.
Now I can. You're gone for a second.
So let's see what we get.
I am doing yes,
41 times sine of 26, closing the parentheses on that sine function, dividing by 25, and then closing the parentheses on the inverse sine function. And we get 45.97, and if I round that to the nearest tenth of a degree, I get 46.0, or I guess just to the nearest whole degree, so 46 degrees. Okay. Alright, so B is 46 degrees. And we can come over here now and find angle C up here at the top. And we'll do that just by using the fact that they all add up to 180 degrees. So angle C will be 180 minus 26 degrees minus 46 degrees. And we get 108. 108 degrees. Great, okay. And now we can finish up this solution by finding side C. We'll use law of sines to find the length of side C. So C over sine of C is equal to A over sine of A. That means that side C is A times sine of angle C divided by sine of A, which is, let's see, 25 times sine of 108, 108 degrees, divided by sine of 26 degrees.
Yeah, me too. I plan to go visit my sister. Nope. I'm staying here.
And we get 54.24 centimeters. Okay. So this finishes up the first triangle, the triangle where angle B is acute. And if we didn't realize there were two solutions, this is the one we would automatically just find, because it's, you know, we get the acute angle B by using arc sine. Arc sine will only ever give you an acute angle. So now we're going to find the second solution. And the second solution is where angle B is obtuse. So I'm just going to kind of redraw that. I'm going to take, you can sort of see that second triangle here in this figure, and I'm just going to take that and draw it again. And this time I'm going to call this angle B prime and C prime, and side B prime and side C prime. Angle A and side A are the same. And actually, that's side B, that's given, so that doesn't change either. But as I change, if angle B is obtuse, I'm going to give it a different name. I'll call it B prime, and then obviously that's going to change the value of angle C as well. In the scenario where we're finding the obtuse solution, the solution where this other angle is obtuse, the new angle B prime is just the supplement to angle B that we found before. So angle B prime is 180 minus 46 degrees. And that gives us 134 degrees. And so then angle C prime they all have to add up to 180. So 180 minus 134 minus 26. We get 20 degrees. Okay, so we have this angle, and we have this angle. So I didn't have to use law of sines again to get angle B. And in fact, law of sines could never produce the, an obtuse angle of 134 degrees. So once I do the kind of the hard work using law of sines to get angle B in the first scenario, I can kind of just use that result to get this new angle. I do need to use law of sines, however, to get side C, right? So, or C prime, right? So little C prime over sine of angle C prime is equal to A over sine of A. So little c prime is equal to A times sine of c prime over sine of A. So this is, let's see, side A is 25 sine of 20 degrees divided by sine of 26 degrees. I get 19.5 centimeters. And those are the two triangles that can be drawn that satisfy the given information. Okay, so let's try one more in this section. Again, you'll notice I know two sides and the angle opposite one of those sides. I have a given angle of 62 degrees, which again I'm going to put on the lower left. Side B, I'm going to put side B along this side here, 855 meters. So angle B would be somewhere, out here. And then angle A, side A is 415 meters. So this is another kind of ambiguous case where we're not quite sure if I can make a triangle, and if there's just one solution or two. And we start this process by finding the height of the triangle. So h is an absolute minimum on how long side A has to be, side little a has to be, in order to even be able to make a triangle. So we get to use SOHCAHTOA on that because that's a right angle. So sine of A is equal to h over side B, sine of 62 degrees is equal to h over 855. That means that h is 855 times sine of 62 degrees. And we get 754.9 meters. So now compare this. Side A is 415 meters. Side H here is 754 meters. So A is too short, right? A is less than H. That means that there is no solution. A is simply not long enough to make a triangle at all.